individuals. In our last class, we talked about the symbolization of alleles. So in this class is actually a continuation of a previous class where I taught about the Mendelian or monohybrid ratio. So I told you that it is not in all cases that you have the 3:1 phenotypic ratio, that there are some exceptions based on some phenomena. So this class I'm going to be discussing what causes those modifications to that 3:1 monohybrid ratio in the F2 individuals. So first, okay, there are broadly two modifications to this ratio. We have the 1:2:1 phenotypic ratio, and then we have the 2:1 phenotypic ratio. So I'll be taking them one by one. Under this, there are two phenomena that cause this modification to this ratio, and that is incomplete dominance and codominance. Okay, I'll be taking them one after the other. First, incomplete dominance. This occurs in a situation where the alleles in a heterozygote or a hybrid individual kind of blend in the F2 offspring. That is, the F1 individuals, when you mate them, their alleles, they are not completely, one is not completely dominant over the other. They both express themselves but are blended in the phenotype of the F2 individuals. So I will give us two examples, one that applies to plants and then the other that applies to animals. Okay, example of incomplete dominance in plants. Let's say we have pea plants and we are hybridizing them and we are considering the traits of flower color. So let's say the first individual, I'm going to be using the uppercase lowercase symbolization scheme. So the first individual has, let's say, white flowers, is homozygous dominant, has white flowers, and the other parent has sorry, this should be, excuse me please, this should be, yes, white flowers, and this has red flowers. So when you cross these two individuals, you have the F1, this will give, these are the gametes, these are parents, gametes will produce, okay, they'll produce these gametes which will join to give us F1 individuals that will all have this genotype. So then, if you are to self-fertilize the F1 individuals, the F1 plants, I have this, and this would also turn out to be white flowers. Sorry, they will be pink. sorry, we have this white, this red. So their F1 progeny will be this. They will be showing pink flowers. So you see there is a blend here of the white and the red flowers. So if you were then to cross or to self-fertilize these F1 individuals with pink flowers, what you will be getting is, if you are to cross this, you'll be having that is this in combination with this, give you this. Then you have as this in combination with this, give you this. This in combination with this, give you this. And then this in combination with this will give you. So here you have one white flowered pea plant, assuming we are considering a pea plant. Then here you have two pink flowered pea plants, and then one red flowered pea plant. So you see you have a phenotypic ratio of 1:2:1 in the F2, as opposed to the 3:1 ratio, because here we have, instead of here, if it were in a completely dominant, if this allele was to be completely dominant over this, what you would have is all the children, all their offspring here would have white flowers. But in this case, they have pink flowers, which is a blend of the white and the red flowers. So this is one of the modifications to this ratio, which is caused by incomplete dominance. Now, the second phenomenon, or the second modification to this 3:1 ratio, like I've mentioned before, is caused by codominance of alleles. In this case, the alleles are both dominant. That is, they both express themselves in the phenotype of the F2 individuals. They are both seen as distinct phenotypes. They might be combined, but they are distinct. There is no blending in this case. There is no blending like in the incomplete dominance. Yes, I remember I told you for incomplete dominance, I'll be showing you the example in relation to animals. Sorry, let me go back to that before I come back to codominance. It's just to help you easily understand this, or understand it better. Okay, for animals like in chickens, let's say the color of their feathers, you cross a black feathered fowl or chicken, let's say black feathers, white feathers, and then have the white feathers, assuming the white feathers are the recessive have the recessive alleles for feather color. So if you cross these two individuals, all the F1 will have white feathers. So let's say, yes, no, sorry, they will have blue feathers. Blue feathers in the F1 individuals. So if you were to mate two F1 individuals, you will be having this with this would give us the black feathers. This with this will give us this. This in combination with this will give us this, and this in combination with this will give us this. So here we have, once again, one black feathered fowl as out of every 4 chickens. Blue feathered, 2 blue feathered chickens, and 1 white feathered chicken. So here again we have that 1:2:1 ratio as opposed to the 3:1 ratio because of incomplete dominance. Okay then, so back to our codominance that I was talking about before I came back here. In codominance, in codominance, the alleles are both expressed in the phenotype of the hybrids. So what we would have is, what example do I use? For instance, in the ABO blood group system in humans, some individuals have the A-type blood, which shows that their red blood cells have the A-type antigens on their surface. We also have the individuals with the B-type blood, that is, they have the B antigens on the surface of their red blood cells. Now, we have individuals with this genotype, that is, they have both antigens on the surface of their red blood cells. They occur together. Let me use a small sketch to illustrate this. Let's say this is the red blood cell, and on its surface we have, these are the A antigens. Okay, these are the A antigens, and then on the red blood cells of the B type, the individual with the B type of blood, have the red blood cells having this. So in AB individuals with the AB blood type will have this on the surface of their red blood cells. So this shows you that they are both expressed, the allele for A-type blood and the allele for B-type blood. Both of them are expressed on the surface of this person's red blood cells. So this is where we have codominance. Now we are done with the 1 is to 2:1 phenotypic ratio. I'll be going to the 2:1 phenotypic ratio. What causes this modification is usually lethal alleles. That is, alleles that kill or cause the death of the individual carrying them. Most times, the dominant lethal alleles cause the death of the individual mostly before they reach the childbearing age or sexual maturity. The individual will die. But that is when they are in the homozygous condition, they kill the individual or cause the death of the individual. Then when they are in the heterozygous condition, what they do is that they cause severe developmental problems for the individual carrying them. And then recessive alleles, recessive lethal alleles, these ones only cause the death of the individual in the homozygous condition. That is when the two alleles of the person were recessive and they are lethal, then the individual will die. Okay, let me give an instance to help us understand this better. In chickens, there is a dominant allele which results in serious or severe, profound developmental problems or developmental issues which result in aberrant forms. That is, they don't appear or are not the way they should be. So that is denoted by an uppercase C. And like I told you, it's a dominant allele. So this allele gives rise to the kind of chickens we call creepers. That is in their heterozygous form. Called creepers. They have short and crooked legs and are of little or no value. So, and then we have the normal chickens with normal size or shape of legs. It's a normal. Okay, so when this dominant allele occurs in a chicken, what happens is that the individual will die. But when it's in this form, it will be a creeper. Like I told you, if a dominant lethal allele will cause death in the homozygous condition, and then in the heterozygous condition will cause severe developmental problems. Okay, so now to show this ratio, you cross a creeper with a normal bird, what you'll be getting is this, and this will give you a creeper, another creeper, and then that's two creepers, two normal birds. Or if you were to reduce it to the lowest number, you have one creeper, one normal bird. But then, if two creepers were crossed, you will be getting this ratio instead of this, and I'm going to show you how. If you were to cross this, we have this and this, this and this, this and this, then this and this. So this is These two are creepers. These two, this one, sorry, is normal. It's normal, but this will die off, leaving us with the 2:1 ratio. So now you've seen how a lethal allele, a dominant lethal allele, has given us the 2:1 phenotypic ratio in the F2. Okay, remember this 3:1 ratio is in monohybrids. Yes, so all this is happening in a monohybrid cross, where we are considering only one trait, alternative forms of only one trait. So these are the modifications to the 3:1 phenotypic ratio. I hope that in the course of this class that you've learned at least what causes modifications in the 3:1 ratio, and you'll be able to teach someone if the need arises. So if you like this video, please don't forget to share with your friends, hit the like button and subscribe to our channel so that you can get more and more videos like this that you can learn a lot from. Okay, thank you very much for watching. See you next time.